Even after the absolute value function has been transformed in some way, maybe translated left or right or up or down, maybe narrower or wider, maybe facing in the other direction, we can still write the piecewise version of these graphs using the same techniques that we saw in the introductory video. So I see in this particular version of the absolute value a clear distinction between the two parts to the left of 3 and to the right of 3. Obviously, if you had this function available to you, this would be a much easier task, but we can operate under the assumption that you wouldn't have that. Looking at the two different parts of the graph, we're going to determine the key information for graphing those lines. First, we know that when we write our piecewise, we're going to split at 3 and before 3. Well, after 3 and before 3. We see that the two line segments meet at 3, so we're not concerned where to put the equal to. As I go to write my equation for the two halves of the graph, I need to be very careful about how I set my intercepts and how I find my slopes. If I'm looking at the right-hand side of this graph, I'll see that I have a vertex at 3, 1, and I also have an intersection over here at the point 4, 4. Calculating the slope between those points gives me a slope of 3. Because I know the symmetry of the absolute value function, and I know that this point over here is at 2, 4, I can guarantee that I have slopes of -3 for one half of the graph and 3 for the other half. And I just need to make sure I put those -3s and +3s, those -3s and +3s in the correct places, because there will be occasions, and we're going to look at one in just a moment, where the graph is actually going the other direction, and whoever the side that's originally negative actually turns to positive and vice versa. So we want to make sure we put those -3x and 3x in the right spots. The difficult part that remains is the calculation of the intercept, the calculation of the y-intercept for both lines. Obviously, if I zoomed out a little bit, I'd be able to see where the y-intercept was for the left half of the absolute value function. But the truth is if I don't have that necessarily available to me, if I don't have that capability available to me, I need to come up with some other way to do it. And that's where the vertex comes into play. So you know going in that when you write the equation of a line, that you're going to have a slope and an intercept. So for right now, I'm just going to call these both B1 and B2. Then I'm going to need to figure out the intercepts of both of those lines. But I also know that the point 3, 1 is on both of those lines. That meeting point, that vertex, that bottoming out point, that minimum point exists on both of the lines. So if I carefully substitute in those 2 points, or those 2 coordinates, into each of the lines, I should be able to figure out what B1 and B2 would be, knowing that I have to go through the point 3, 1. You'll have to excuse me on that one. I want to make sure that I use the 1, because that's what's actually going to allow me to solve the equation. Solving both of these equations gives me B1 is equal to 10 and B2 is equal to -8. I can go back, erase my stand-in B1 and B2, and add in a 10 here and a -8 there. For the sake of conversation and discussion, probably wouldn't be a bad idea to graph both of those lines just to make sure that we ended up in the correct spot. So here's -3x plus 10, which goes right over the left half of my graph, but we of course needed to stop at 3. And here is 3x minus 8, which goes right over my right half of the graph, and of course we want that one to start at 3.